Hello, everyone. So in this week, we're going to cover the binary dependent variable model. And this model is about chapter 11 of your textbook. So make sure that you read the textbook along with the videos you have for this week. We also have homework 3, which is posted today. We have quiz 3, which will be posted for 24 hours on this Friday. Okay, so you have here the slides and you have the videos for this topic. Okay, so what I'm gonna do today, like this week, I'm not going to go over this topic actually, which is the binary dependent variable, because all these videos are actually covering this topic and they are kind of enough for the information I wanted to deliver for this topic. However, I will leave these videos for you to watch for this week. And next week, what I'm gonna do is to do some applications based on my assumption that you guys have watched the videos, okay? Again, we have here also a practice which is related to this topic. I encourage you to do it for extra credits. Okay, so 3 points extra credits, and this would accumulate for your final and midterm. Okay, we have this in-class practice. You have here a PDF file with the questions, the data that you will need to use, and the data description, because as I said, each data set has its own description. So you will need to actually read the description before you start working on the questions. Okay, and this is the same with the homeworks, exams, and any stata application. And by the end of the day, I should be posting for you the link of the stata part. Okay, and these are the this is the data DTA file and Excel file and the data description for the homework. Okay, and remember, you have also a discussion for this week. Okay, so what I'm gonna do actually today, since I said I'm not going to go over actually this topic, I'm going to continue our topic of last week. And our last week topic, which was the nonlinear models. So in the nonlinear models, we covered the polynomial models in the lecture. So this was last week lecture. We covered the polynomial models. I gave you 2 homeworks. It's just like an equation to solve for today's class. So I hope you guys have done it. And I'm gonna give you the solutions by the end of today. Okay. I would also encourage you to watch the log models on stata and interaction models. So what we have covered in this topic about nonlinear models is the polynomial models, and I started an introduction to the log. So today I'm going to continue the log, and also I'm going to go over the interaction models. Okay, so let's start. I'm going to share with you my iPad. So in the iPad, okay, just wait, it's supposed to work. Okay, so okay, so so we started already the Parth and Dan. So you guys are late for today's class, okay? So make sure that you arrive on time, because I will start anyway on time, because we have so much to cover in this course. So make sure that you arrive on time so that you do not miss any explanation. All right, so I'm going to start again from this slide. And in this slide, we said last time that we have three different types of log models. We have the linear log, we have the log linear, and we have the log-log model. And always the first term, refers to the y, and the second term refers to the x. So y is linear, x is in log, y is log, x is in linear, or both are in log. And we said last time that log models are actually used if you want to talk about percentages, right? So you want to actually use percentages in your analysis rather than just using dollars and cents and miles and so on. All right, so let me start from here. So log models, the main use of it is that basically is the conversion, or it converts the changes in variables into percentage. I'm going to write it this way, percentage change. Okay, so when x is small, so when x is just a small number, right? So when x is, for example, just 1 point, okay? So if x is just 1 point, so in this situation, I will be using the log model. So let's say, so when the change in x is small. So you always have this rule, okay? So it basically says that the old value of x plus the change in x, this would give me the new value, right? Which is the old value plus the change. If I subtract it from the old value of x, then I will get the approximation to a percentage change. Okay, so if you even can try this on a calculator, and if you try it on a calculator and you try to just plug in some numbers and you say, okay, what if I have the change in x is equal to 5 units, and suppose that the original value was 100. So if I ask you a question without knowing any econometrics, and if I ask you a question, I say, what is the percentage change in x? All what you need to do is to take 5 over 100 and you multiply it times 100, right? So you would say, okay, the change in x over x is 5 over 100, which is equal to 0.05, and you have it in your mind, okay, it's 5%. Okay, so this is if I multiply it times 100, okay, the change in x is 5%. You can do the same exact thing if you use the rule. So whatever you have here, like this thing, is actually this thing. And I said that this ratio is approximately equal to this subtraction, okay, or this formula. So I can repeat this by saying, okay, it has to be equal to log 100 plus the change minus the original value of 100, right? So that means it has to be the same as log, or natural log 105 minus the natural log of 100. And if you plug it on your calculator, you would find it equal to 0.0487. So whatever I get out of this equation, right, is the same as whatever I get out of this ratio. Why? Because based on this rule, they are approximately the same. Okay, so when I get from the first rule, when I get it as 0.0487, I can easily say, okay, this is approximately equal to whatever I get of 0.05. So based on this topic, which is the log models are used in order to approximate the changes in X into a percentage change. So it converts the changes into percentage change. Whatever you get out of this rule is the same as whatever you get, or approximately equal to whatever you get based on what you already know, which is the change in X over X. So I'm going to write this formula again because this is something very important, and this is what we are going to use multiple times in this topic. So we said that the log of X plus the the change in X minus the natural log of the old X is approximately equal to the change in X over X. And this is our rule that we will use now many times. Okay, so let's start our different types of log models. We said we have a linear log, a log linear, log. So let's start with the first one. What about the linear log model? So it's linear in Y, log in X. So a linear log model would look like this. Yi is equal to beta naught plus beta 1 log xi plus ui. And this I like goes for over like n people or n countries or n whatever the type of cross section that you are using, okay? And now suppose that we consider this one as our equation for y before any changes, okay? So this is the original no change. Now, suppose that I decided to change x and see how it affects y. So if I decided to change x, then if x changes, my new level of x would be x plus the change in x. I still have an error term, I still have an beta 1, beta naught, and anytime x changes, y also is gonna change. Okay, so I wrote it backwards because like it matches what we think about. A change in x brings a change in y. So now let's call this one as equation A, and this is equation B. So if I want to finally know what is the impact of x on y, then it's going to be the equation B minus equation A to get the change in x, the change in y, which is our dependent variable, right? So to get the change in y. So to do that, we basically subtract So when I subtract this part, so I'm gonna have yi will cancel with yi. So I'm left with the change in yi, okay? Now, when I subtract b from a, the beta naught is gonna cancel, okay? Next, when I subtract b from a, I do have a common factor of beta 1. But what I have inside the bracket is log x plus the change in x minus the log of x, right? And of course, the ui would cancel with the ui. And based on what I know, I'm gonna call this star because this is important equation or formula that we will use. So based on that, I can always, anytime I see this term, I can remove it and plug in this term. So I can say, okay, the change in yi is equal to beta 1 times the change in x over x. And this is based on equation star or formula star. And now we come to the final point, which is my interest would be, okay, what about the slope? So the slope, which is beta 1, is equal to, just solve for beta 1. So it's going to be the change in yi because of the change or the percentage change in xi. So this is a percentage change in x, okay? And this is what we have for a linear log. So anytime I'm giving you a model and I'm asking you what is the impact of the change in x on y, remember that you will use this formula. So let me give you an example. Or I wanted to just make one final note that suppose that, like, look at here, this one here, okay? And suppose that y or x changes by 1 unit, because every time we deal with, like, every time we use 1 unit change, right? We keep saying, okay, it's a small change, so let's say we make it 1 unit. So if x changes by 1 unit, and when I say 1 unit and it is in percent, then it's 1%, okay? So the change in y for a 1% change in x is equal to beta 1 over 100. In other words, you can say that the change in y is equal to beta 1 multiplied times 0.01. Okay, so anytime I have a linear log model, and if I'm asking you a question about, okay, what is the change in y, then change in y is going to be equal to the partial slope attached to the x multiplied times 0.01, and this is for a 1%. What if I ask you 5%? So for the 5%, just I'm sure that you know that. So if it is 5, just remove this and this, and it's gonna be like, okay, 5% change in x, which is 5 over 100, would bring 0.05 times beta 1 change in y. And I'm sure that you understand, okay, what is the value of beta 1? It's the estimated from stata or the estimated from your regression model. Let me give you an example. So this example, linear log, I have, I need to estimate the factors affecting the minutes of sleeping or sleeping minutes. And we have estimated a model, so this is hat. And the intercept is equal to 5022.82 minus 232.6 1 log total work. I'm gonna write it like this abbreviation, total work. So here we're trying to estimate how the increase in the percentage minutes of work affects the minutes of sleep or sleeping minutes. So this is percent minutes, so x is in percent, y is in linear, is just in minutes. So if I'm giving you a model like that, and I'm asking you, what is the effect of a 1% increase in total work? So this is the total work in minutes, okay? How many minutes you work per day. So a 1% increase in total work would bring 232.6 times 1 over 100, which is 0.01, and this would give you 2.326 minutes. And remember, the sign is negative, right? So that means if a 1% increase in total work, sleeping minutes decrease by 2.326, or you can approximate and say 2.3 minutes. Okay. notice that when we write our analysis of these types of models, I have to make it very clear that X is in percent. So that's why I'm saying 1%, and Y is linear. Okay, because otherwise when I'm grading your work, I'm like confused whether you understand it actually or not. So you have to make sure that the units of measurement for each variable is very clear and it's written. Now, do you have any questions?
No.
Okay. Now let's go to the next model. And again, I want you to remember that we will still keep our formula, the star formula, okay? So this star formula is very important because we are going to use it in each and every model we are referring to. So let's go to the next. So number 2, log linear model. So a log linear model would be like log y is equal to beta naught plus beta 1 x. Okay, so I don't have any I don't have any nonlinear measurement for x, it's just in the y plus ui. Now suppose that I change x. So for any change in x, so beta 1, if x changes, right, then y is going to also change, right? So it's going to be the log of y plus the change in y, right? Now, again, this is A and this is B. So B minus A to get the change in the percentage change in y. So if I subtract this part from this part, then it's going to be, okay, log y plus the change in y minus log y equal, beta naught is going to cancel with beta naught. Then I'm going to have beta 1 multiplied times the log, x, right? It's going to go with the x. So I'm left with the beta, I'm left with the change in x, or the delta x. So delta x, okay? Now, again, my interest would be about the change, okay? So based on the formula, I know that I can remove this part and write it this way. Change in y over y is equal to beta 1 change in x, okay? So that means the slope would be beta 1, just solve for beta 1, would be the percentage change in y because of a 1 unit increase in x, whether it's in minutes or dollars or miles or anything, okay? And I want you also to notice that every time I have a model like this and I'm talking about x as linear, my answer has to be in percent, right? So I give you a question, what is the $1 increase in x? Your answer has to be in percent to reflect that y is in percent. So let's see this example. Now I have y is in log of wage. And this is the model we have for today's practice, wages. And then we have an intercept 578 plus 0.067 experience. So this model is trying to find how experience, or the years of experience, so this is in years, this is in percentages, right? So how the additional years of experience would affect the percentage change in wages, okay? It makes sense to say that the additional years of experience would have an increase, or wage would have a percentage increase, okay? So if the question is if experience increases by 1 unit, and my unit here is years, okay? So if experience increases by 1 year, okay, what happens to the percentage change in experience, okay? So based on what I have here, look at this. Okay, I'm going to just take it on the other side. So this one is saying that the change in y over y is equal to beta 1 change in x. Now, if I want to analyze this in terms of percentages, I want you to remember this is in percent. So if this is 1, then this is 100. If this is 5, then this is also 100. All the time, whatever I have down here is 100, right? So I can actually write it this way: the change in y is equal to beta 1 change in x times y. And I can make it easier and write it this way: the change in y is equal to beta 1 change in x times 100. Or write it, I prefer to write it this way: the change in y is 100 beta 1 change in x. Okay, so now 1 year is here, so this is 1. Beta 1 is here, so this is beta 1. You just multiply it times 100 and get the answer. So the change in y is equal to 100 times 0.067 times 1. Then your answer would be 6.7%. Remember, you have to add the percentage symbol. Okay, so a 1 year increase in experience would bring 6.7% increase in wages because the sign is positive. All right, any question? Next, suppose I have, and this is the easiest one, log. So I have log y is equal to beta naught plus beta 1 log x, okay? So what I have here again is, if you think about it as, again, you're changing x, you can also have the UI, or you can just remove it, it's going to cancel anyway. So any change in x, any change in x, right, would be reflected in a change in y. Okay, now this is like this. Now this is again A, this is again B. Then I want to know what is the change in y. So the change in y would be B minus A. So I'm gonna have on this side the log y plus the change in y minus the log of y equal, these two would cancel, right? I have a common factor, beta 1. Then I have this big bracket of log x plus the change in x minus log x, and the error term is going to cancel. And what I can do is look at the star formula and replace these two. So the star formula would tell me, okay, this part is the change in y over y equal to beta 1 change in x over x. Now, when I have anything in percentages, I know that this is 100 and I know that this is 100. So I can easily remove these two, right? Because they can cancel together. They are the same number. So I can say, okay, the change in y is simply beta 1 change in x. And this brings us back to our normal slope that we know, right? I can just easily read whatever I see in the regression output without multiplying by 100 or dividing by 100, because this is actually what I know. This is what I know about the slope, which is the change in y due to the change in x. And that's why I'm telling you the log-log model is the easiest, because actually it's the same as what we know from how to analyze the slope of any just linear model. So let me give you this example. So this example is an example of the elasticity model, price elasticity of demand, PED. The price elasticity of demand is the most famous log-log model in economics. So it's about the demand for certain good hat. So it's estimated it's equal to 551 minus 67 price. Okay. And let me write here, I forgot the log. So this is log demand and this is log price. So it's a log-log model. I'm telling you it's easy to analyze this model because I can easily say a 1% increase in price implies 67% drop in demand, right? So I'm telling you it's the easiest because you just take this coefficient and you just add the percentage symbol. You don't have to multiply times 100 as we did with the log linear, and you don't have to divide by 100 when we had it with the linear log. You just take the number, add the percentage symbol. Okay. So you guys have any question?
All good.
Okay, so having covered the three types of log models, the question would be, okay, how these models look like, okay? So I know that in our first introduction to econometrics, we had a linear model, which is, okay, this is y and this is x. This is just a linear model. Now, when we covered the quadratic model, we said that we are adding some nonlinearity and some bends to the model. So the relationship in the quadratic model, for example, which is a type of polynomial models, would be like, okay, like this. Okay, what about the models that we covered today? So this is y linear log in x. This one would actually look like a polynomial. Okay, it looks like, I should say not polynomial, I should say it looks like a quadratic, but it has some flat towards the end, so some flatness towards the end. So it's like this and it gets like more flat. This one I should like have, this one has more of a curvature. Okay, so it might not be very easy to see, but it has like some curvature. Okay, this one like goes like this and gets flat. Next, okay, what about the log? So this one is linear log. This is log linear. The log linear would be like, okay, y is in log x is linear. It's actually very close to a linear shape. And the last one would be, okay, what about the log model? And this is log in x affects log in y. And this one again has some curvature. Okay. So when we either draw these types of models, especially 1, 2, and 3, might not be able exactly to determine which one is the best fit because they actually look very similar, right? For our eyes, they look very similar to us. Unless I can see all the dots and I can actually determine which one is the best fit, but actually this is also a hard job because it's not that easy to just look at the eye and determine whether they cover all the points or not. But econometrics offers for us a certain test to determine, okay, which one should I use? Is it linear? Is it log linear? Is it quadratic or linear log or log log? Because for our eyes, they look the same. So the best answer to that is the following. So how to compare models? Which model is the best fit for our regression? I have so many different types. We said I have linear, I have linear log, I have log linear, I have log log. Okay, and I can keep adding quadratic to the power 3 to the power 4, can add interaction after recovery. So the best answer would be, you can only compare models when the dependent variable, which is y, has the same unit of measurement. So this one, y is linear, right? This one, y is linear, right? This one, y is in log. This one, y is in log. So I can only compare models when the y has the same unit of measurement. So I can only compare the linear with the linear log. I can only compare the log linear with the log log because they do have the same unit of measurement. And choose the one that has the higher R square or adjusted R square. Same goes here. Compare between these two models, choose the one that has the higher adjusted R square because this would imply that it has a higher explanation to the model. Okay, you can never compare a a linear log with a log linear because y here is in is linear and this one is in percentages. They cannot be compared. So just before comparing models, just make sure that you do have the same unit of measurement. And in order to do this, you have to actually estimate your model and get the results of the adjusted R square and then say, okay, this one is better fit for my regression. Okay. All right, so I gave you a couple of examples while I'm explaining. What I'm gonna do next is just to give you like a brief summary of everything I mentioned, because I know like log models is just one of these challenging models. So let me just have one brief summary here. So the model is linear log. So yi equal beta naught plus beta 1 log x plus ui. How can I interpret that? Okay, so the interpretation, so this is the model, this is the interpretation. So a 1% change in x implies change in y. Okay, so you have to take your coefficient and you have to whatever if it is 1%, 1 over 100, if it is 5%, then 5 over 100, and you multiply it times the estimated beta, right, to get the change in y. Number 2, for the log linear. So log y equal beta naught plus beta 1 x plus ui. And here I'm going to say a 1 unit. When I say unit, here can be dollar, can be cents, can be miles, can be minutes, anything, okay, but not percent. So in x, I am sorry, I 1 unit change in x, 1 unit change in x, okay. Let me have it clean. So a 1 unit change in x implies 100 beta 1, right? And you add the percentage symbol. Change in y. So you have to multiply times 100, add the percentage symbol. Okay, remember here we didn't add the percentage symbol because y is linear, so I don't need a percentage answer. Last one, the easiest. So log, so log y beta naught plus beta 1 log x plus ui. So here again, a 1% change in x is associated with beta 1. You just add the percentage sign, change in y. That's it. Okay, so I think it's clear now, and I hope you don't have any confusion about the interpretation of these models. All right. Okay, let's do next. So what we have next is the interaction models. Okay, so with the interaction models, and this is like the last part of the nonlinear models, and as I said at the beginning of today's lecture, for the binary dependent variable model, I want you to watch the 4 videos you have under this week. Okay, so the interaction models, what's the idea of an interaction model? So if I have a model like this, yi is equal to alpha naught plus alpha 1 xi, or let's say x1i plus alpha 2 x2i, and I stop here. So suppose I have this model, and this model is telling me that, okay, alpha 1 would show me the effect or the change in y due to the change in x1 holding constant x2. So x2 is held constant, okay? Now, what about this one is the same. So it would give me the change in yi due to the change in x2i holding constant x1. So suppose that this is your salary, or the salary or the wage of a person. This is the let's say education, years of education or years of schooling, and this is the years of experience. So each one would have a separate effect on y, but I might be interested in their simultaneous effects. So then there's simultaneous effect. So what if I'm interested in certain years of education complemented with certain years of experience, okay? So I need 2 things happening at the same time. In order to do that, we will need to update this model by adding an interaction term. So plus alpha 3 x1i times x2i. So this interaction term is showing me the effect of x1 on y in the presence of x2, or the effect of x2 on y in the presence of x1. So interaction term, and this one is called interaction coefficient. Okay, so interaction term and interaction coefficient, and is used to give us the simultaneous effect of x1 with x2. All right, so we have different types of interaction models. We have like 3 types, and let me write them here, and then I'm going to go over them in details. So we have basically 3 types of interaction models. All right, so I have, first of all, I have interaction between 2 dummy variables, right? I have interaction between 1 dummy variable and 1 continuous variable. Okay, and I can have here 3 different cases. The first case is, what if I have same slope, different intercept? What if I have the opposite, different slope, same intercept? And as you might expect, so it's different in both, different slope, different intercept, right? And then the last one, interaction between 2 continuous variables. Okay, so let's start with the first one, which is I have 2 dummies. So let's see this example. So let's start with interaction between 2 binary variables, okay, or 2 dummy variables. So suppose I have this model. So I have yi is equal to beta naught plus beta 1, d1i plus beta 2, d2i plus ui. And I want you to imagine that so far I don't have any interaction terms here, right? So let's see, and you know that this one would represent the effect of d1 on y holding constant d2, and d2 would and beta 2 would represent the effect of d2 on y holding constant d1. Now, if I want to add an interaction term, then I would have to update this model by adding a multiplication of the 2. So plus beta 3 d1i multiplied times d2i plus ui. All right. So again, this is the interaction term or the interacted regressor. You can call it interacted regressor or interaction term, it doesn't matter. So suppose that D1, it's a dummy, so it's going to take like 1 or 0. So suppose that D1, it takes 1 if the person is female, and it takes 0 for male, and suppose we have just 2 gender types. And D2 is the binary or the second binary that takes 1 if the person is a college graduate, and it takes 0 otherwise. All right, so now we need to analyze the following. What is the effect? And I forgot to mention that this is earnings, okay, or log earnings. So this is how much they earn. So this is earnings. So I want to analyze the effect on earning due to having a college degree or not. Okay, so if I want to see whether having a college degree affects my earnings, then I have to see the impact on Y for the presence of D2 versus the non-presence of D2, right? So if I have this model with D2 and versus the model without D2, then the subtraction of both models would give me the effect. It's exactly like the idea of taking the first derivative with respect to D2. But these are binary variables, so we cannot take a first derivative, right? Because it takes only 0 and 1, doesn't have anything in between. It's not continuous variable. So if I want to see what is the effect of college degree on earnings, which is Y or Y. So in order to do that, so the first thing is, okay, what is the effect of no college degree? So when D2I is equal to 0, I plug 0 everywhere I see D2I. So the model would be yi hat would just be equal to beta naught plus beta 1 D1I. So this is the model if the person has no college degree. Okay, now what if the person has a college degree? So D2I would be equal to 1. And I plug it in the model and I'm gonna get, okay, I'm gonna get yi hat is equal to beta naught plus beta 1 D1I plus beta 2 times 1 plus beta 3 D1I times 1, right? So this means that it's basically equal to, let me combine like terms. So constant, let me just add the hats everywhere because this is an estimated model. I keep forgetting adding the hats, okay? So now, I didn't add the hat here because I have an error term. So this is like the main model, the population regression model before the estimation. Now let's combine them. So I have a constant here and I have a constant here. So my new constant would be beta naught plus beta 2, right? My new intercept would be beta hat 1 plus beta hat 3 D1I. Okay, so this is the regression for college degree. Now, if I want to ask you what is the effect of a college degree, then I'm going to have, okay, this is equation number 1, this is equation number 2. So the effect of college degree would be 2 minus 1, and this would be like, okay, 2 minus 1, the beta naught would cancel, so I'm left with, so the change in yi hat because of, or the change in earnings because of having a college degree would be beta hat 2, this is the new intercept, and then this term minus this, the beta 1 would cancel, so I'm left with, this is beta 3, all right? So this is beta 3. So I'm left with beta hat 3 D1I. So the effect of education or college degree depends on gender. So like looking here, okay, this would give me the effect of having a college degree, and this would give me the effect of a college degree in the presence of type of gender. So I can actually make this more specific and say, okay, what is the equation for males and what is the equation for females? So we said that this dummy will take 1 for females and take 0 for males. So for the females regression, or if the person I'm talking about is a female, then the additional wage is going to be equal to beta hat 2 plus beta hat 3 times 1, which is beta hat 2 plus beta hat 3. And remember, this is in dollars, okay, because this is the change in earnings. And if I'm talking about if the person is a male, so this is the change in yi is equal to beta hat 2 plus beta hat 3 times 0, then this is beta hat 2. Okay, this is the impact or the final amount of additional dollar for additional year of education for a female applicant, and this is for a male applicant. Okay, and it's in dollars based on the, if I'm assuming that y is in dollars. Any question? Okay. Next, suppose I have, so this is number 2, interaction between 2 dummies or 2 dummy variables or 2 binary variables, whatever. All right, and in this model, I'm gonna have like, right, 2 dummies interacted at the same time. And again, let's keep the same story. Y is the earnings, okay? And did I say 2 binary? Wait, I didn't. Oh, we already had 2 binaries. Okay, we are still here. Okay, let me give you actually, let me actually give, before I start the next one, I'm gonna give you an example. So suppose this example, I have earnings hat is equal to 590 minus 20.4, dummy for females, that takes 1 if the person is a female, 0 male, plus 150, dummy for experience, that takes 1 if experience is 3 or more, minus 35, dummy female multiplied times dummy experience. And let's define these dummies. So df takes 1 for female, 0 male, d experience takes 1 if experience is greater or equal to 3 years, and 0 otherwise or less than 3, strictly less than 3. Okay, so I wanted to look here and I wanted to imagine that you basically have 4 cases. So the person can be male with 3 or more experience, female 3 or more experience, or a female with less than 3, can be a male with 3 or more experience, or a male with less than 3 years of experience. So I have actually 4 cases. So anytime you have 2 dummies in a model, I want you to think of 4 possible cases, and you can come up with 4 different cases. So I want you to think about worst case, assuming discrimination between males and females in the labor market, and the best case. Of course, can someone tell me what is the worst case? And these are intermediate points. So what is the worst case? I do have here every case. I have a dummy for female and a dummy for experience. dummy for female, dummy for experience. So let's see. So if I'm assuming that females earn less, and of course with small number of years of experience, then it's even worse. So what do you think the values for DF and DE? What about Dan? You have an answer?
DF.
Bart?
Wouldn't DE be less than 3 or 0?
You guys, I can't hear you. Can you type in the chat? I think I have a problem with my mic. Guys, can you hear me? Because I can't hear you. Wait.
Yeah, I can hear you.
Less than, yes. So I just want to make sure, guys, that my mic is working.
Yes, we
So
can
let me
hear
know.
you.
Can you hear me?
I
I
can hear
can't
you.
hear you guys. Like nobody's talking. Just want to make sure. Are you guys quiet or okay? You can hear me perfect. Can you try your mic, please? Just say anything.
Hello, hello.
Because mine is not working. Like I can't hear you. Yes, so I cannot hear you. Yes, that's a problem. Okay, I'll figure out this after the class. I do get a notification from Zoom that I need to update my audio settings, so I'm gonna do that right after class. So anyways, if you have any question while I'm talking, since I can't hear you guys, just type on the discussion forum. And yes, so then let me continue here. So the worst case, as Dan typed, and as you guys said on the chat, so here the worst case would be like a female, so this one has to be 1. So this one has to be 1. You might, okay, 1, and less than 3 experience. Okay, and then this definitely would be like a male with more than 3 experience. And then I do have like 2 intermediate cases in between, which are not, we are not 100% sure which one is stronger. Is it female or experience, but which is the factor of female versus the experience. But definitely you can do that. You can look at the coefficient here. Experience by itself increases your earning by 150, but being a male just 20, right? So it seems that experience is stronger, right? The fact of having experience is stronger. So the intermediate case would be here. This is a male and experience is less than 3. And this is a female and experience is here. So we plug in the 1s and 0s and you will get these numbers. So you will get earnings here would be, if you plug 1 and 0 into this equation and you solve for the earnings, you would find earning is equal to 569.6 and then 590 and then 6846 and then 740. And when I say best case, because I see the earnings are the highest, and the worst because the earnings are at their lowest point. Okay, Okay, so this is about an interaction between two dummies, right? So I have a dummy and I have a dummy and I have their interaction. We're done with this part. Our next case would be, okay, if I have, which is number 2, what if I have interaction between one continuous and one binary or dummy variable. Okay, so suppose I have this model. So yi is equal to beta naught plus beta 1 xi plus beta 2 di plus ui. And let's assume, okay, this is again earnings. And this is experience in years because it's a continuous. And this D is gonna take 1. Let's make it for males. It doesn't have to be females every time, males. And then 0 for otherwise or for female because we have only 2 gender types. Okay. Now, if I'm asking you, can you check if the effect of experience on earning is the same for both gender? Like, can we check that? So if the effect of experience on earning is the same, by looking at this equation, the answer is yes, because this is experience, right? And this is the effect of experience on earning, and it doesn't seem to be different from both gender because it's not interacted with the gender type. Okay, so let's see. If di is equal to 1, then this is the equation for male, a male worker, for example. Then the yi hat would be equal to beta naught, right? Plus beta 2, because beta 2 is multiplied times 1, I can combine it with the intercept, plus beta 1 x. Why I wrote here x1, this is, you can think of it as xi, okay, which is the experience. And if di is equal to 0, then this is the equation for females, and yi hat is equal to just the beta naught plus beta 1 xi. So if I'm asking you, is the impact of experience is the same? Yes, because the beta is the beta. So if I don't have any interaction term, then actually both gender would have the same amount of additional earning for each additional year of experience. The only thing I want you to notice is, I want you to notice this part. See this intercept versus this intercept. The intercept for the male models versus the intercept for a female model. So this one is telling me that this is the amount of earnings in dollar that a male person would get if experience is 0, right? So at 0 experience, then you plug in xi equals 0, then this part is gone, this part is gone. I'm left with just the intercept, and this is the definition of an intercept. So if I, at experience 0, males earn beta naught plus beta 1, beta 2, okay? Beta naught plus beta 2 dollars, and females earn on average, remember everything is on average, right? Beta naught dollars. So this is what we call a model with same slope, different intercept. So despite the fact that the effect of education, the effect of experience is the same for both gender, at 0 experience, they earn different amounts. And this is why, because I'm setting up this model such that the coefficient attached to the continuous variable is the same, which is beta 1 for both gender, but I do have a dummy which is added to the intercept, creating a new intercept. Okay, now what if I want to have a model that would show me something more realistic? I want to have a model that would show me that additional year of experience implies a different amount of earning depending on the gender type. Okay, and this is more realistic because this is what we know. It's like what we know in the US market and many other countries is that it's not only the case that at zero experience males and females earn differently, or males earn higher than females, but it is also the case that for each additional year of experience, earning is not going to increase by the same increments or the same amounts. So in order to do that, we have to introduce a new type of a model in which I have different intercept and different slope. So this is second case, right? Which is different intercept, different slope. And just to not get lost, so remember, everything is still under this big topic, right? Which is the interaction between one continuous and one binary. We discussed the first case, okay, which is same slope, different intercept. This is, let me write here first case. This is the first case. And this is our second case in which we have different intercept, different slope. And I actually prefer this model because many applications, it's more realistic. So this model, in order to be able to get different intercept and different slope, I need to add a dummy because this one would be added to the intercept of the model, creating a new intercept. But I also have to have an interaction term that it's going to affect the impact of experience, okay? So in order to see that, so basically, again, we're gonna do it the same. When di is equal to 1. So when di is equal to 1, I'm going to get the male regression. And when di is gonna be 0, then I'm gonna get the female's regression. Okay, so the di1, this is the male regression depending on our definition, and this is going to give me, just plug in 1 everywhere, combine the intercepts beta 0 plus beta 2 plus beta 1 plus beta 3 xi. Now if di is equal to 0, I get the female regression, and the female regression is easier when I plug in 0 because everything is gone. Everything that has a di, this is gone, this is gone. I'm left with just this part, right? So yi is simply equal to beta 0 plus beta 1 xi. I want to compare this one versus this one, okay? So when I look here at the females, at the male regression, at 0 experience, they earn differently, right? So at 0 experience, males earn beta 0 plus beta 2, females earn beta 0. So this is at 0 experience, okay? What about additional year of experience? For each additional year of experience, right? males earn beta 1 plus beta 3. Females earn beta 1. This is more realistic, right? Assuming that all these coefficients are positive, assuming like all of these, like I need to have the hats everywhere. These are like the estimated model, assuming this is the estimated model. So that means at zero experience, we earn differently males and females, but also for each additional year of experience, the slope is different. So this model is a case in which I have different intercept and different slope. And I prefer, again, this type of model in many applications because it's actually more realistic, right? When I talk about labor market discrimination, it's not about zero experience that we earn, that we have males are earning higher, but it's also for each additional accumulation of experience, the slope is higher for males versus females. Okay. All right, so let's talk about the third case. We discussed the first case where I have a same slope, different intercept, different slope, different intercept. Now, what about case 3, where I have same intercept, different slope? Okay, same intercept, different slope. So in this case, let's have a model where I have yi is beta naught plus beta 1 xi plus beta 2 xi times di plus ui. Now, again, if d is equal to 0, this is the female's regression, right? So yi is equal to beta naught plus beta 1x. If di is equal to 1, this is the male regression, then it's yi is equal to beta naught plus beta 1 plus beta 2, right, xi. Now, again, at 0 experience, they earn the same, okay, which is beta naught dollars. So they earn the same at 0 experience, which is not realistic because we know, like in the job market, we know there is a discrimination. So even 0 experience does not imply that they earn the same amount of dollars. And for each additional year of experience, we have 2 cases. For males, they earn beta hat 1 plus beta hat 2, and for females, they earn just beta hat $1. Okay, so that means we have same intercept because they earn the same at 0, but we have different slope because for each additional year of the continuous variable, which is experience, they do earn differently. Okay, any question? Okay, if you have any question, again, type on the chat because I can't hear you guys. Okay. What we can do, okay. I'm gonna give you an example. I'm going to show you a few things in the example, and I'm gonna ask you to do a homework for next week. Okay, so let's see. Suppose I have this log model, okay? So this is log linear. So I have log earning is equal to 6.92 minus 3.13, dummy for age, binary variable, minus 0.019, age, continuous variable, plus 0.085 age multiplied times dummy for age. Okay, now let's define the dummy. So this dummy variable is a binary variable dAge that takes 1 if age is less or equal to 39, and it's going to take 0 otherwise, or if age is strictly greater than 39. So this model, I'm using it in order to be able to differentiate between people who are 39 years of age or less and people who are older than 39. And so this is a dummy. For the age, it's a continuous variable. Okay, so it's like, okay, 21 years of age, 22, 25, 30, whatever. So it's just like not a 0 of 1 variable, but it's a continuous variable. Now, this interaction term is here in order to do the differentiation between people who are above 39 and people, or people who are 39 and less, and people who are strictly more than 39. Okay, so if I ask you, what is the earning equation, or what is the regression for if age, or for age less or equal to 39? Okay, and what is the regression if age is above 39? So one regression, I'm going to plug in di. So this one implies that d age is 1. This one implies that d age equal to 0. And if I plug 1 and I combine, then log earning. I read log earning as learning. Okay. Log earning is equal to 6.92 minus 3.13 multiplied times 1 minus 0.019 age, right, plus 0.085 age times 1. So there is another 1 here multiplied. I want you to combine any number. So if you leave for me a question, and if you leave for me the equation this way, you will lose points, because you will have to combine all the numbers together, all the slopes together. So that means your final answer would be like this: log earning is equal to 3.79 plus 0.066 age. Okay, and for if age is equal to, this is easier, right? So here's 0, here's 0, so I'm just left with this part and this part. So in this situation, log earning is equal to 692 minus 0.019 age. Okay, and so basically this regression predicts a negative relationship between age and earning only if age is above 39, and a positive relationship otherwise. Okay, so a positive relationship otherwise, which is if age is equal or below 39. Okay, now I can use this regression to answer many questions, and these are the questions that I want you to answer. So write the null hypothesis for the following test. It's not a question mark, it's just, okay, write the null hypothesis for the following tests. Number 1, and this is your homework for next week. I want you to write the null hypothesis for testing whether age above 39 has the same effect as age of 39 or below. I want you also to repeat, write another null hypothesis that tests whether the two regression lines have the same slope. 3, test whether the two regression lines have same intercept. Okay, so this is your homework for next week, and we're going to discuss your answers. And again, I don't want to give you the answers now. I can easily like go over them and give you the answer, but I just want you to think about it. I want you to write your answer in terms of a null hypothesis like this, okay? And see what is the coefficient that you need to test and whether it's equal to 0 or it's a joint test. Probably it's a joint test, okay? So maybe I'm testing more than one coefficient, so you will need to find out or figure it out, and I'll ask you next week. Okay, the last type, it's the easiest type, which is the interaction. I'll discuss this one and I'll give you like 5 minutes break. So number 3, interaction between two continuous variables. So this one is the easiest, and I'm going to tell you why. So I suppose I have beta naught plus beta 1 x1i plus beta 2 x2i plus beta 3 x1i multiplied times x2i, and suppose that, again, this is earning, this is experience, and this is education, okay? And now suppose that I want to find out what's the impact of experience on your earning. I can easily do a first derivative. So what is the impact of experience, or what's the first derivative of this equation with respect to experience? Then it's going to be equal to beta 1 plus beta 3 x2i. So the effect of experience on earning depends on education. So your education is a factor into this slope, right? So effect of experience on earning would depend on the level of education, right? So this is a type of a continuous, of a two continuous variables. I'm saying it's the easiest because in order to find the effect, I don't have to find like when D1 is 1, when D1 is 0 and take the difference, because it's a continuous, two are continuous. So I just take the first derivative of the equation and it's easily like would easily give us the answer. Okay, so this is the end of the interaction models. I'm not spending time on the two continuous variables because it's the easiest, as I said, to find out their impact. Let me give you like a 5 minutes break. I'll be back at 2:03. Okay, and then after I'm back, I will continue this topic, but showing you the stata application. All right, so I'll be back in 5 minutes. right, everyone? So what I'm going to do next is I'm going to share with you my stata file, and I'm going to show you some stata application. Before we move to the stata part, I just want to double check. You guys have done the homework that I told you of last week. So it was about the exact and the approximate effects. So just before we leave the iPad, so we had a model. Where is it? Okay, so we were talking last week about the turnaround point. Okay, this model. Okay, so I gave you last week this model, and it was a polynomial model in which I have experience affects wage, and the relationship was quadratic. So what I did for you is I solved this model for the change in experience from 0 to 1, right? Okay, so this was the model. So what we did, yes, we had two types, an exact change and an approximate change. Okay, and what I did for you is I did it for the change in experience from 0 to 1 years. I did it by the exact change where you plug in the 1 squared, right? And you subtract it from the model where you have the 0. Since you guys, I can't hear you, so can you tell me your answers for the exact change? I asked you to do 2 to 3, and I asked you to do the 0 to 7. So please type in the discussion forum your answer. I'll give you like a few seconds to type it. So I asked you to do, okay, let me see. Okay, 2 to 3. So Parth is saying that from 2 to 3 he got yes, from the 0 to 7, but the 2 to 3 I got a different number. I got 0.2675. So this is what I got. So let me know, maybe I have a mistake, or you can try it again. So this is the, let's have it like that. So I asked you to do from the 2 to 3, right? And this is the exact, and this is the approximate. Okay. What I have, what about Dan? What did you get? So from the 2 to 3, I have it for the exact as 0.2675. And from the 0 to 7, I have it as, yes, as Dan got it, so 1 point. Actually, I have a few decimals difference. 7871. Okay. Dan, did you get the answer for the exact changes? Type in the discussion forum. Okay, for the approximate, What are your answers for the approximate? Okay, for the approximate, 2.27. What? No. No, for the approximate, just yes, okay, all right. So 0.2736. Okay, we agree on this one. Okay. And then from the 0 to 7, and we agree on this one too. Great. 2.086. Okay. So can you just, after class, just redo the exact again and double check the numbers you have? And I'll do the same on my side, but I'm almost sure that my numbers are correct. Okay, what we can say from here is, if the change is small, like 2 to 3 is just 1 year of experience. If the change is small, then the answer of exact versus the approximate is almost the same, right? It's very, very close. However, the numbers gets wider, get far away from each other for big changes. From 0 to 7, it's like 7 years jump. Okay, so the approximate versus the exact change will not give you exactly or approximately close numbers. Okay, so anytime you have a question about the exact versus the approximate change, what you need to do is just check your question. If that question is asking you for the exact, then do exact. If I'm asking you about the approximate, then do that as the question is saying. But if I don't give you in the question what you do, you have 2 options, either exact or approximate. If the change is small, like by 1 unit, then either or, exact or approximate. If the change is big, then you better go with the exact, not the approximate. Okay, so the exact changes is safer to use versus approximate when the changes are big. Okay. Before I leave this slide, I just want to make sure. Okay, we answered this already. I want to make sure that you still remember this. Okay. Okay, Parth is saying my answer is right. Okay, thank you for the confirmation. Okay, you saved my time. I was going to double check. Okay, thank you. All right. Just remember, anytime you have a quadratic model, I would ask you about the turnaround point, and this is what we're gonna do in stata now. I want you to remember that the turnaround point is computed by this way, by this formula, right? So the turnaround, the point at which x moves from being negative to positive, is solved, like as we did it last week, as the absolute value of beta 1 over 2 beta 2. Okay, so what we're gonna do now is I'm going to go to stata. I'm going to show you how to determine the degree of polynomial when I have a quadratic model, like whether it's a quadratic is better than cubic or power 4 is better than both. And we're going to compute the exact changes, and we're going to compute the turnaround point. Okay, so hopefully after I'm done, I'm going to leave you with the practice to do, and we'll discuss it. So let me share my desktop again. Okay. I have many do files that I can use. So let me choose one of them. So let's see. Okay. So this one is, okay, let's try this one. So this one is a sleep data set. It's trying to, as I was talking about in the example I gave you, is trying to analyze the relationship between the sleeping minutes, okay, and the total hours of work, or total minutes of work, the age, the education, education squared, education cubed, education to the power 4, and we're using a robust standard error because the model has heteroscedasticity problem. Of course, we're not going to check heteroscedasticity here because we already done with this topic, and I'm assuming that if you have this model and I'm asking you check for heteroscedasticity, I assume that you know how to do that using the BP test. So, and then after you determine based on the BP test that you need robust, then you will add robust standard error to your regression. As every time what we do is, okay, I don't have the, okay, so I already said, well, I already described the data, so it's about sleeping minutes. I usually have the description of the file, but it's okay. All right, so let's use the data set. Okay, so we have the data set. Let's describe it, summarize it. This is usually like without me asking you, like you would need to look at your data set just to know, okay, age, the youngest person is 23, the oldest person is 65 years of age. Black is 0 or 1, so it's 1 if the person is black. And education starts from 1 year to education to 17 years of education, and so on. So, and then we have the, where is it? Okay, the description is right here. Okay, so you have this label. Okay, so the age is in years, 1 if black, clerical if clerical worker, construction worker. So you have everything right here. We're not going to use all these X's or all these variables. We're going just to focus on a very small model for today's discussion. Okay, now suppose I want to perform a block test to check for nonlinearity. I want to answer a question. Is the sleeping minutes is linear or nonlinear in age? Okay, so do you sleep more or less when you get older? Is the change in the sleeping minutes is the same as you get older? And it makes sense that it's not the same. We see like usually older people sleep more than younger people. This is on average, like this is just an observation, okay? So assume that I'm asking you to use a log model, a log linear model. So that means my Y, which is the sleeping minutes, is linear. So I want to generate a log version of that variable, right? So you basically, it's not in the data set. So you would generate the variable, and you need to check by using block test for nonlinearity up to degree 4. And usually, as I said, even if I'm not telling you in a question, what is the highest I can go for the degree of polynomial, just go to up to 4. So my data set already has the age square. I have seen it somewhere. Yes, it's right here. See, its age square is already here, h to the power 2. So all I need is just to create or generate to the power 3 and to the power 4. And after you do so, you add all the nonlinear age terms to your regression, okay? And the robust standard error towards the end. So after you're done, you just regress it and you get the answers here. We're using a block test, so I need to do an F test on 1, 2, 3, because if these 3 are 0, then the model is linear in age. So I want to check whether those 3 are jointly statistically significant or not. So to do that, you basically perform an F test, right? So an F test would be on the 3 terms or the 3 nonlinear terms. And based on that, what you can see here, it is always like easier to look at the p-value. So there is a 52.13% probability that those are equal or jointly equal to 0. And if this is the case, this basically means that most likely those are equal to 0. This is a very high probability because it's 52%, right? It exceeds the 5, it exceeds the 10, it exceeds all significance levels. So you're safe to say that my model, based on the block test, my model is linear. It's not up to 4. The question was linear or non-linear. and your answer based on the block test, it is definitely linear, because there is a high probability, 52%, 0.13 probability, that those are jointly equal to 0. Okay, so just get rid of them. However, if we do more specific test, okay, so this, based on the conclusion here, as I said, my model is linear in age. Now, suppose that I want to perform a more specific test, sequential, I take it in sequence. I start with a model up to 4, right? And then I minimize it. So I start up to 4, and then I minimize it up to 3. I'm sorry, my computer keeps jumping. And then I take it up to square. And each time I'm just checking the t-statistic of the very last coefficient. So when you do that, let's regress the 3 together and go to the first one. Look at the H4, statistically insignificant. Then all what you need to do is to drop it and re-estimate a model of degree 3. Look here, insignificant. Again, conclusion, we fail to reject, re-estimate the model, right, with r equal to 2, which is quadratic. What we have here is, you know what? Yes, what we have here is insignificant, okay? So you came up to the same conclusion that based on the, we drop the h square and the model is linear. So my best fit for this model would be actually like, this is the best fit, which is a model is linear, and you remove this part and your model is simply linear, and that's it. Okay, so what you did is basically you took it like in order. So age is statistically significant, and based on the specification of this test, the model is linear in age. Okay. Now, suppose that I want to do more, let's see, let me do house price. Okay, what is house price? This is another story, okay? So you have a model in which you're trying to analyze the prices of houses in a certain district, okay? So you collect the data on the prices of houses, the square feet of each house, how many bedrooms, how many bathrooms, how old is the house, whether the house has a pool, whether the house has a waterfront. Okay, I'm gonna skip everything. I'm just gonna go to what I need because there are so many details here. There was a turnaround point that yes, it's right here. So suppose that I want to estimate the model. Let me first clear what I have, because otherwise Theta would give me like a an error message. So let's clear and get the new data, right? Describe and summarize. Now we have the new data, and the main model was just a linear model. We performed heteroscedasticity test. We decided that we need robust standard error, right? This is not what I want. Suppose that I'm going to estimate it in terms of a log linear, right? So I need to generate a log for the price. I'm just like letting you know the discussion. You don't have to worry about all this. And then suppose that I'm asking you to create a polynomial term in bedrooms or quadratic term in bedrooms. Well, the idea is additional bedroom increases the price of a house, yes, but each additional bedroom would not have the same impact on the price. The price would increase from 1 to 2 bedrooms and from 2 to 3 bedrooms with a certain amount, but it doesn't have to be the same as from 4 to 5 bedrooms, okay? Most probably the price would change, or the additional increase in price would be smaller and smaller and smaller. So let's see the effect of adding a polynomial term. So let me first get the log of the price, because otherwise I would get a message saying you don't have L price. And let me also get the log of the square. Do I need that? Just a second. Yes, the log of the square feet. Okay, so it's a log in square feet. And I want you to see this combination. Okay, log price, log square feet, quadratic in bedroom. So it's an expanded model that has log, quadratic. Now, let's add a square term for the bedroom. Okay, and now let's regress our model. So our model is, let me expand this one and show you. So our model is log price, log square feet, bedroom square, bath, age, pool, waterfront, and robust standard error. Okay, so we run this model and we extract the coefficients. So what I need is, I regress the model and I can see statistical significance, and I see that bedroom decrease the price at an increasing rate. Okay, and then I see that all these coefficients are statistically significant, even the square term, so the model is quadratic. And I need to determine what is the cutoff point. So the cutoff point, which is the turnaround point, is computed using these coefficients, right? I need the coefficient of bedrooms and I need the coefficient of bedroom square. So all I need to do is to get these coefficients out of the estimation result. To do that, you can use the command scalar. You call this any name you like, you can call it your name, but everything here has to be exactly the same. So underscore B, I'm asking stata to go to the matrix of coefficients, which is called B, and get for me the coefficients of bedroom. And make sure that the name that you see here is the same as the name that you see here, or you have it here. Next, you need to do the same for beta square, and you extract it from the model. And then you compute the turnaround point. You know that the turnaround is the absolute value of beta bedrooms over 2 multiplied times bedroom squared. So you can compute that, right? Because we have already extracted these coefficients. You simply need to compute and display. So when you look here, this is the equation and the display is right here. So turnaround value for bedrooms is 4.55 whatever, so it's around 4.56 bedrooms. There is no fraction for a bedroom, so you can say it's around 5 bedrooms is the cutoff point. Okay, you can actually make more space here so that you don't have like the sentences. So okay, so this is very important because I can give you the data set and I'm asking you to get the turnaround point. Of course, you know the equation for the turnaround point. You get the beta of the coefficient divided by 2 times beta squared of the coefficient that is polynomial. You don't have to extract the coefficients unless I'm asking you in your assignment to extract them. It's very important and it's very, very helpful to learn how to extract the coefficients using the scalar command, because it makes your life easy and it makes your presentation of the results nicer. Okay. What else? Let's see this. If I'm asking you, what is the approximate effect of the change in the number of bedrooms from 5 to 6? So remember, we have like dependent variable is in log. So, and then the variable I'm asking you about is linear. So it's log linear. Anything that I'm gonna get, I have to multiply it times 100 and add the percentage symbol. So the change from 5 to 6, remember this is the equation I gave you in class last week for the approximate change, okay? Which is basically the beta of the coefficient of x plus 2 times the beta of the coefficient squared multiplied times the original x, and then outside is multiplied times the change in x. Now the change is from 5 to 6, which is 1, so that's why you don't see here the multiplication times 1. Okay, so this is the approximate. And now you can do it again from 6 to 7. You can nicely display your results here by saying, okay, I generated a variable called 5 to 6, which is simply the approximate change based on the equation I gave you for the example of wage and experience on the iPad. So all what you need to do is to take this 5 to 6 number and write it into your display command and add the percentage symbol. And you can repeat the same for the other one. Okay. So let's see that. So, okay, 5 to 6, you just get this and you get the display. So the approximate change in price due to the increase from 5 to 6 bedrooms is 2.4 whatever percent. So you can say it's about 2.5% jump in the price for the increase in bedrooms from 5 to 6. From 6 to 7, the jump in the price is much bigger. It's about 8% jump in the price. Okay. What else we can discuss here? Adding interaction. So what if I want to know the effect of having a pool and a waterfront together on the change in price? Like the model that I have here, let me just maximize this. So the model I have here, as you can see, this is the effect of pool, of having a pool on the price of the house. This is the effect of waterfront on the price of the house. What if I want to have the simultaneous effect of pool and waterfront? So I need to have a multiplication between the two. And based on our labels and the summary that we have done, which is at the beginning, where is it? Okay, let me do it again. Just want to show you that describe. Okay, it's not complete. Okay, anyways, so pool is 1 if yes. So pool is 1 if you have a house, if you have a pool in the house, and waterfront is 1 if yes, meaning if it's 1 if you have a waterfront. Okay, so both are dummy variables. So I'm going to do an interaction between two dummy variables. Okay, so the interaction term, you can generate it, you call it anything you like. Anything you like. I prefer to start with an int so that I know it's the interaction between the two variables. And you just add it to your regression. Okay. And after you add it to your regression, you need to figure out whether you actually need this interaction term or not. So if I'm interested in the effect of waterfront, okay, and the interaction of pool with waterfront, then I need to do the test PRM, which is the F test. And the F test is telling me that there is a 0 probability that these are equal to 0. In other words, keep the interaction term in the regression along with the coefficient of waterfront. Any question? Okay, so based on the F test, yes, keep it. Now, what I need to do is need to answer a question that say, if I'm asking you what is the predicted percentage change in price when a pool is added to a house with waterfront. So you need to get out of this regression the effect of the waterfront, the effect of pool, okay? And these are the scalars, so you generate them and answer the question. So, okay, remember the price is in percent, so I will need to, and the waterfront is linear, okay? So you will need to multiply times 100 and add the percentage symbol, okay? So the answer is here. So if I have a pool and waterfront, then I have 18.47% increase in the price, okay? Do you have any question? Again, you don't have to extract coefficients unless I'm asking you to do so. So let's say in today's practice, which I'm asking you to go now to Sakai. Okay, I'm out of Sakai, but you can check the practice here. And the practice is under week 6. So when you go to Sakai, get the practice. You have a data set which is called wage 2 DTA. Okay, I want you to get this data set in your stata, which I assume that you already did, since I sent you an email 2 hours before the class with the data. I asked you to have stata ready. So I want you to do a regression, regress the log of wage on education, on age, non-white, union, and female. And I want you to answer what is the increase in log wage if age increases from 25 to 26 years of age. And I'm asking you for the exact. So you just plug in. I want you to use the sequential hypothesis to determine if age is to the power 4, 3, 2, linear. I want you also to use the block test to determine if it is 4 or linear. Okay? Finally, I want you to use a log quadratic model in log age, education, age, non-white. Okay, and then log quadratic model in the age variable. So that means I want age and age square. Okay, I want you to estimate the turnaround point and the exact changes if age increased from 25. So I'm repeating the same question here. This question was for a linear model. Now it's for a quadratic model. Okay. So I showed you on the on my do file how to estimate a turnaround point. You don't have to extract coefficients, right? You just need to regress a model similar to this, here again with a robust standard error as the question is asking you, but this is different data set, this is different story, okay? You're using the wage data set, here I'm using the price data set. And you don't have to extract, if you want to extract it, if you have a nice presentation, I always recommend that you extract coefficient. And it just like, once you learn it, that's it. It's going to be easy to use later on. And I want you to compute the turnaround point. If you cannot extract the coefficients, or if you're not extracting the coefficients, then just compute it like on a piece of paper. The turnaround point, and these are the approximate. You basically plug in for the exact. Okay. So I will leave this open here for you. I'll give you like 10 minutes and then I'll come back to check on you. Do you have any question before I leave? I'm gonna just give you like 10 minutes. Again, type on the chat if you have any question. You have the data sent to you by email. You have the data again on Sakai. You have the description of the data set on Sakai under week 6. All what you need to do is take the data into stata, estimate the model as I'm asking you in question 1. Estimate the model using robust. So your model would have to, where is it? Your model would have to end with an R for a robust, okay? And then you have to answer this question for 25, which is just 1 unit change in age. Easy, read the coefficient. Use the sequential hypothesis. How to do that? So here I showed you sequential. You start with R4, 3, 2, 1 to determine whether your model is linear or of a certain degree. And what else? Block test. I showed you the block test. Block test, you have all the polynomial terms, again, up to 4. and then perform a test, PARM, which is an F test. What else? Turnaround point. I showed you the turnaround point, right? You extracted based on here, or you can compute it by hand. All right? Any question? Okay, so now it's 2:39. I'll get back to you at 2:50. Okay, 11 minutes. 2:50. Okay, I have a question here. Yes, the questions are available in Sakai. Can you see it? Just go to week 6. You will find like a title which says in class practice, and it's a PDF file. Can you find it? Just confirm here. Okay, Dan, thanks. Okay, perfect. So just open the questions. I'll leave the do file open here for you on the sequential test. And which one? Let me show you this one. So this one, you have the sequential test. Okay, you have the performing a sequential test and performing the block test. Leave this open here. For the turnaround point, you can compute it by hand and just give me a number. Okay, so I'll be back in 10 minutes. Hi everyone. So part is saying the variables in the description don't match with the variables in the stata file. Okay. Okay, let me check. Are you guys able to do the estimation? I'm looking for the description of the data set, but yeah, I mean, like you can still work on the estimation. I think the variables are self-explanatory, so you don't have to worry about the definition. You can even label them until I find the description for you. So type on the discussion forum if you have any question. So I just checked, it seems to me they are the same. So we have wage, female, non-white, union, education, experience. So you guys were able to do the first question? Were you able to find the variables? Just let me know in the chat. You're done with the question one? So the command gen is for generating, is for creating variables, okay? Generate, gen is for creating variables. You should have watched my introduction videos for the stata videos on my website. I mean, not, I mean, on the course site. Okay, so let's review the questions. Okay, guys, so let me start, where is it, the question in class practice? Okay. Part, let's start part take question 1, then 2, part 3, then 4. Okay, so let's start question 1 with part. Are you done with the estimation of the model? No. Okay. Do you have any issues, any problem? Like you can get the variables, right? The problem with the variables, you mean like don't match, like with the variables that you have are not the same as the ones I ask you to regress? Okay, so you don't have the data. Okay, all right. So let me try to send you the data in a few. So I'll stop this share so that I'm able to send the data. Okay, I'm just trying to figure out. I know that I have 2 sets of wage to DTA. So let me try to figure out which one. I think I found it. So I'll email it to you right now. You guys should have told me like before the break, because I sent you this data set. Okay, so I just sent you the wage to the DTA. So can you download it and let me know if it's matching the variables now? So check your email. And please confirm on the chat if it's the same now as the description that you have of the variables. It's the right file. Perfect. Thanks, Bart. So so we have about 15 minutes left for the class. I'm not planning to cover anything new. As I mentioned at the beginning of the class, the binary dependent variable model, you have the videos for it already here. So I'm not planning to record anything new. For this week topic, you just watch the videos, and I'm going to do application for it next week. For now, I want you to work on, like I'm waiting for you here. I just want you to start the questions. Okay, so this is the right description now, which is great. Okay, so what I want you to do is, let's do question 1 and 2. Okay, and the sequential, and I'll keep 3 and 4, like depending if we can cover them in the 15 minutes. So let's start 1 and 2. So Parth is gonna answer 1, Dan is gonna answer question 2, and I'm gonna have the file or the do file open here for the sequential, which is about question sequential, and the block test are right here. All right. Let me give you 5 minutes, since you already now have the correct data. I'll give you 5 minutes, and I'll ask you for questions 1 and 2 before we move on. So how are we doing? So are you done, guys? So let's take question. Let's take question 1. So let's ask Parth. Parth, have you done with the question 1, which is just a simple estimation of the model? Okay, great. So what is your answer for the age increase by 1 unit on the percentage change in wage? What's the number you got? So we need an exact effect of the increase in log wage, which is the percentage change in wage, if age increased by 1 unit, which is from 25 to 26. Okay, just a second, fine. And we're using a robust standard error. Dan, did you get the answer for question 1? It's, remember, the wage is in percent, right? So we need an answer in percent. So what's your answer for the increase in age by 1 unit on the percentage change in wage? Okay, so you're saying 0 or 0.012. Let me check your answer. I can't, I don't have it on top of my mind. I would have to run my answer. So what I have here is the wage data set. Okay. We have a log linear model, which is this one. And it's log wage on education, non-white, and so on. What I did is I do extract my coefficient so that I have it in a nice way. So we need a generate. So Dan was asking me what is gen? Gen is generation or creation of a new variable, right? So I want to create a new variable. I call it log wage because my model is a log linear. And I do regress log wage on education, non-white and female. And we get a certain regression, okay? You don't have to extract the coefficient. You can just look here. And as Parth said, he just went to this coefficient and he said, this is the answer. However, the correct answer, since this is in percentages, I have to multiply this coefficient times 100 and add the percentage symbol so that I can read it as a 1 unit increase in age, how it affects the percentage change in wage. So I did that right here, okay? So I extracted the coefficient. You don't have to do that, but I highly suggest that you learn, because sometimes in an exam, this might not be an option, okay? So you have to learn it because it's an easy, but it just requires you to learn it first. So I got the scalar, and then this is your question, okay? Because I didn't ask you about the 50 to 51. So let's actually, let's display both, okay? And when you go here, so what the answer is the coefficient that Parth said. He said 0.012, but I need to multiply it and add the percentage symbol. Okay, so it's 1.276%. If the age increase from 50 to 51, I do have the same number. Why? Because the model is still linear in age. As long as the model is still linear in age, then I do get the same slope. It's constant slope. Okay. All right. So so this is for question 1. Is Dan here can answer question 2? Dan, did you answer question 2 for the sequential hypothesis test to determine the degree of polynomial? What degree of polynomial did you find for the log equation or the log of wage equation? I think I have my code wrong. Okay, you think you have your code wrong? Okay. All right. So Parth, did you work on question 2? Parth? No, I'm working on it. Okay. So you know what, guys? Now it's the 3:17, so it's almost the end of the class. What I want you to do is, this is our work for next week. So we're gonna start with this next week. You come to class answering 2, 3, 4. Okay, in a do file, and I want you to have it ready for our next week. So we're going to start with that, and I'm going to correct it and give you the correct answers. Yeah, and so I'm going to stop here. Do you have any question before I leave? And remember, you don't have to extract coefficients at this stage, but I want you to learn it for the midterm. I want you definitely to learn it for the final exam. Any question before I leave? Okay, thanks, Parth, and thanks, Dan. And let me know if you have any question on the discussion forum. I will be grading your homework 2 discussions, and you should be seeing your grade book complete by the end of this week. All right. Remember our topic for this week, which is the binary dependent variable. I'm not going to lecture it live. I already have it in recorded videos under week 6. So this is required. So I want you to watch the videos, take notes, and next week we're gonna practice it. Okay, we're gonna practice the binary dependent variable model. All right, everyone. So enjoy the rest of your week. See you. Thank you, and make sure you come in class on time. Okay, so just log in 12:20 sharp, because I'm gonna start anyways. Whatever you missed at the beginning of the lecture, you will see it in the recorded file. Okay, but I want you to come on time. All right, see you next week. All right, bye.